So let's start with computational problems. Just a quick overview, what they are and their types. So what is a computational problem? For uh, number one, they are problems with well-defined inputs. Secondly, they have a set of conditions and these conditions will help us arrive at the solution of the problem. Third thing, well-defined outputs. So you have inputs, you have a certain conditions that have to be met, which lead you to the outputs. The types of computational problems, you have 5 types. One, decision, yes or no problems. Deciding whether a number is even or odd, prime or composite. Those sort of problems are decision problems. Search problems, finding an element in an array, finding the maximum element, so on. Counting, the number of given elements, number of the given element, the number of possible solutions to a, say, Sudoku. Optimization, the best solution by some metric. For example, if you want to go from point A to point B, you can optimize by time, you can optimize by distance, you can optimize by fuel. So it's finding the best solution according to some measurable metric. Function problems. These transform the input into the output. Based on some set of rules. So sorting is a function problem. You take in an unsorted array and transform it into a sorted. Okay, so computational problems, I hope that's enough of an overview. Moving on to computational costs. Now, computational costs is what is the foundation of complexity analysis, which we will get to later. So the idea behind computational costs is we want to optimize. To optimize, we need to know where to optimize. That is where in a given computational problem or algorithm, is it slow or is it taking up too much memory? We can optimize for various different factors. Most commonly, we optimize for the running time and for the amount of space taken. So to optimize, we need to find where the costs are. To find where the costs are, we need to analyze. The first simple method to do this is step counting. You take an algorithm and for each step, you assign a cost. So a step may be an operation or a single line in the algorithm. And then you sum all the costs together to find how much um, the total cost of the algorithm is in time, in terms of time or space. Let's take an algorithm for the sum of first 10 natural numbers. That is, okay. Here we have the algorithm for sum of first and natural numbers iteratively, not the formula based. Assignmenting here it's a cost of 1. Here it's going to be another cost of 1. Here, this while condition, is going to be checked at least n times from 1 till it equals n. And then when I is equal to n plus 1, it will be checked once again and become false. So for n iterations, there will be n checks and then one false check. This thing, you're going to add s and I together and assign it back. So it's 2, and this is going to repeat on each iteration. So per iteration, it's going to be the cost of 2, same deal with I. So the total cost, you just sum it up. 1 plus 1 plus n plus 1 plus 2 times n plus 2 times n, 5 plus 3. Similarly, space cost. Now, when it comes to space cost, there are two types of costs in space. There's only one involved here, so let's just see this first. So we have I variable, S variable, and nothing else. And then the third one is for n. So the input also takes up space and it's also factored into the costs, the algorithm. Now the two types of space costs, let's see. First type is fixed. These are for your input. Let's take linear search. Here, you have two cases, the best, or three cases, I guess, best case, worst case, and anything in between. The best case scenario would be the first element being the element you want. So in that case, this is going to take place as normal. You'll get to the first iterations of these iterations. You'll get to one check, and then this will be true, so it will just return. In that case, there is a cost of 1, 2, and 3. In the worst case, the entire loop will run completely, and then you will return -1. In that case, the cost will be the same as the overall cost, 4n plus 2. So that's best and worst case costs. Similarly, for space occupied, you will have best and worst case costs. But for most trivial algorithms, those tend to be the same. Next, we have asymptotic notations. I'm just going to go off the slides here because they are rather succinct and complete. So, asymptote. What an asymptote is a line that approaches a curve and gets infinitely closer as x tends to infinity. But the two lines never meet. That's what an asymptote is. So, in our step counting, we found a cost, right? Here we just set the cost to be our f of n. And for measuring performance, what we do is we try to get an asymptote to our f of n, which we call our reference function g of n. So we're measuring performance so that we can optimize our solutions to computational problems. So to optimize, you have to look at the dominating factor. You have to you have to look at what takes up the most resources in terms of time or memory or whatever else, and then try to optimize it. Therefore, we look at the dominating factor, compare f of n and g of n. And how we do this is by multiplying g of n by a constant. There are a set of possible comparisons. This is listed here. The ones we will be interested in are defined in terms of big O, big omega, and big theta. So for big O, we have our C times G of n and our f of n. So the C times G of n exceeds f of n beyond a certain point and never meets again, right? So in this regime, we chose, okay, let's actually draw a different. Let me graph y is 9x plus x square. So this is our f of n. And then we have our g of n, which is just taken to be x square. So initially they meet and then they just stay apart because of that 9. Similarly, in this random graph, initially c of n, c times g of n and f of n meet a couple times and then they never meet again. This part is where the other factors, apart from the dominating factor we chose, the other factors dominate. And the point from which they don't meet again is n naught. For all n greater than n naught, c times g of n uh, will never meet f of n again. And for big omega, it's the exact opposite. F of n will always be greater. Here, f of n will always be lesser. And for theta, you have both the upper bound and the lower bound. If you look at the actual definitions, because such that t of n, which is the cost of our desired function, is always less than or equal to c times f of. So this is an upper bound on the performance of our function. And the performance cannot be any worse than this. Omega, on the other hand, is a lower bound. The performance cannot be any better than this, greater than equal to. And theta exists if both the upper bound and the lower bound agree. So if you have a function for which the upper bound and the lower bound is the same, then uh, theta exists and says that the function performs exactly as well as this. Essentially, you're saying the upper bound is less than or equal to performance, which is less than or equal to the lower bound, and upper bound equals lower bound. Therefore, performance equals the common value. Okay, this is the tabulation method to find f of n, sorry, the constant and n naught. We just assume an arbitrary constant, and for a given constant, we try to find the minimum input size and not beyond which g of n grows faster. Here, so for c equals 5, our n naught is 3. Big omega, same idea. You just do the opposite comparison. You pick an arbitrary constant and pick the knot for which c times c of n slower than f of n. And big theta, it is both inequalities together. So the whole thing needs to be satisfied, which again happens at 3. And we're just taking the same constants for omega and theta, 1 and 5. C1 is for omega and C2 is for theta. Sorry, oh. These are some common growth rates just graphed. So log grows slower than linear, n log n slower than n square but greater than n. And then 2 power n is exponential, which is greater than everything else. That's now for an example. Okay, let's take linear search again. Why not? So for any given input size, both best case and worst case can occur. So let's just take the best case first. In the best case scenario, our cost is always going to be 3. So f of n is 3. So we can take our g of n to be, well, 3. There's nothing else you can take. And let's say C is 1.5. C is 1.5. In which case you will get for 1 f of n, C dot g of n, sorry, n, C, 3 times 1.5 is 1.5, which is already greater, and then 2, sorry, 3, 4.5, and this will continue. You can see the pattern will continue. So our n naught is 1 for the C equals. This is where we go. So the cost of our function is of G of n. So here what you can do in this sort of case is this. You can set g of n to be 1 and transfer this 3 over to the constant. So when you do that, it'll be off. And for the worst case scenario, f of n is 4n plus 3. So let's take g of n equals n. For 1, we have 4 plus 3, 7. Oh, I forgot to pick a constant. Let's say c equals say c equals 3. 3 and 3. Okay, for omega, you have to pay the constant so that it always stays below. For O, you have to pick a constant that it always stays above. So for omega, we would pick 3. For O, we need to pick more than 4 because it will be at least 4. Let's pick 5. So 5n would be 5. For 2, you have 8 plus 3, 11. 5 times 2 is 10. For 3, you have 12 plus 3, 15. 4, you have 16 plus 3, 19, and then 20. 5 plus 23, and then 25. So n naught is equal to 4. So n naught exists. So your t of n is equal to g of n equals O of n. And similarly, you can do the same for the worst case scenarios. And for omega, as I said before, you just pick a constant so such that it always stays under. For sorting, searching, and the rest of unit 1, I'm handing over to AJ.
Let's start off with some searching algorithms. We're going to be covering linear search and binary search. So, as we already know, we've already been through linear search. You just compare each element one by one, and then you pick the index wherever you find it. Let's say here, search for 4 in this array, right? First, you'll compare with 1. It's not it. 2, not it. 3, not it. And finally, we found 4 at index 3. So this will return 3. If it is not found, it will return -1 after going through the entire array. So since we are looping through the entire array, obviously this is going to take O of n complexity, right? So generally, it's going to be O of n. Best case will be if you found your element that you're searching for at the start itself, right? So that will be O of 1. Worst case is not finding, in which case not belongs to array. It's not belonging to array. In which case you have to travel to the whole array, which will give you O of n. Space complexity. Um, Auxiliary space is what extra space you need in this algorithm. We'll come back to that after analyzing what's that step count, and we'll count the space also. So first, step count. We can see here assignment cost 1. Comparison, n comparisons plus 1. So this is n plus 1. Okay. Then here 1 per iteration, and this is 2 operations per iteration. If you see, the entire algorithm will take 1 plus n plus 1 plus these two will repeat n times. So n into 3, which is equal to 4n plus 2. This is how you perform step count for this. Similarly, okay, we can also take count the fixed space for this. To find the fixed space, as Narendra has already mentioned, first you have to see what extra variables you are taking to help in this algorithm that does not depend on input size. Here, I is an extra variable you are taking, does not depend on input size. This size is 1 will take. And then you have to include input size also. Here, input size is array size is 1, is n, and then these two are numbers, right? So there will be plus 1 plus 1. So fixed space cost um, will be n plus 3, right? That is in order of n only. So here fixed space is in order of n. We have not used any auxiliary space dependent on the input, so we'll take this as O of 1. I think that covers linear search. Let's take binary search now. Binary search, general algorithm. Okay, first of all, only for sorted arrays, right? General algorithm goes like this. You have your beginning index and end index. You will compute middle of these two, beginning plus end minus beginning by 2. And then you will compare this with the element you are supposed to find. If x is less than the middle element, update end. Otherwise, update beginning. That is, you you first see if x is the middle element or not. Sorry. Otherwise, you will just return. If you found x at the middle spot, you just return that index. After going through everything, if it is still not found, you'll just return -1. Let's walk through this. Let's say search for 4 again. First, your beginning is 0, ending is 4. Middle will be 0 plus 4 minus 0 by 2 is 2. 2 index has 3. Obviously 4 greater than 3. So update beginning. So now new beginning is 3, ending is 4. Update middle. Middle index will now be 3. And at 3 you have found 4. So you return that result. So since at every point you are dividing the array into half and then searching within that half, right? So at each step, you're dividing the problem in by 2. So this will take O of log n base 2 time, right? Again, here now best case will be if you found the element in the middle itself, that is on your first check. So that will be O of 1. Worst case will be if it is not there at all, which will be O of log n. And then we'll come back to space. Okay, step count. Assignment cost 1, 2 operations cost 2. Um, see. Then here low less than equal to high. This will be performed log n plus 1 time, I think. Then inside these will happen. So per iteration, cost for this is 4. Cost for this is 1. Cost for this is 1. And this is 2. This is 2. Let's see. So what happens in uh, generally, worst case, let's take. This will happen for all of the iterations, right? So what will be computed is it will be 1 plus 2 plus this thing, log n plus 1, plus 1. This is not, this check is also happening, yes. Comparison is happening, updation is happening. So 4 plus 1 plus 1 plus 2, 6, 8. 8 into log n, something like this, right? So yeah, you just solve that and you'll get your step count, right? I'm not solving that for you. Again, it will come only in order of log n if you see here also. So that way you can just double check. Let's see fixed space cost. What extra are you taking here? You're taking 1 for low, you're taking 1 for high, you're taking 1 for middle. Other than that, no extra variables you're using, right? Again, input cost here is n plus 1 plus 1. N for array, 1 for n, 1 for x. So that will be n plus 1, 2, 3, 4, 5. 5. So here we can see fixed space is in order of n due to input. Auxiliary space is 1, extra one particular. So yeah, that's binary search. Let's go for sorting algorithms. I think everybody will know this already, but still, bubble sort. This basically concept is n minus 1 passes will happen. At each pass, the biggest element will move to its position, right? Let's take it with example. So 2, 3, 5, 4, 1. Iteration 1. Compare adjacent elements. Is 2 greater than 3? No. Let these stay as it is. Is 3 greater than 5? No. Let it say as it is. 3 also. Is 5 greater than 4? Yes. So you have to swap this. So 4 will come. 5 for now is here. Is 5 greater than 1? Yes. So 1 will come here, 5 will go there. And then iteration 2. Compare again. Now 5 is in its correct position. 2 greater than 3? No. 3 greater than 4? No. 4 greater than 1? Yes. So 4 and 5. These two are now in correct position. So like this, keep going on. 2 greater than 3? No. 3 greater than 1? Yes. So 3, 4, 5. That is sorted. And then iteration 4, which is n minus 1 iteration. 1 greater than 2, no, and it's all sorted. Usually bubble sort, it will always happen for n minus 1 passes, right? But you can put an early stop to it in case the array is already sorted in a previous iteration, right? You just need an extra flag for that. So we can see for each pass, you're traversing through the array once. So for n minus 1 passes, each pass you're going through the array once, meaning time cost will be in order of n square, right? So your time is in n square. Uh, let's see. So here, best case will be O of n square if not optimized. If optimized, it will be O of n, but that is only specific. Worst case will be O of n square only. Let's see step count. So here, this cost 1. 2 operations cost 2 times. How many times this will happen? Um, n minus 1 times, right? Now, each iteration, this costs 1, this costs 2. Inside all of this happens n minus I minus 1 for each I, right? Uh, this cost is 2, 1, 2, 2, 2. So instead of complicating everything doing here itself, let's take it like this, right? You want to compute how many times these things are running in total. So for I from 1 to n minus 2, this is for outer loop. How many times inner one will run? Um, it will go from n minus 1, sorry, I think n minus 1, no, n minus 2, something along those lines. That's n minus 1, n minus 2, so on till 1. First, n minus 1 natural numbers, n minus 1, n minus 2 by 2. And this is the number of times all of this should happen, right? So we'll take that as 1, 2, 3, 4, 5, 6, 7, 9 into 9 for all this internal stuff, plus this will happen n minus 1 times. This will also happen n minus 1 times. So n minus 1 into 3 plus sorry, n minus 1 or n minus 2. I'm not sure about the specifics. Anyways, this will be given, and plus 1 for that. So you can calculate the time cost from this. We'll give the proper step count in a PDF for your reference later. This I'm just explaining, so I guess it's fine. Space cost. How much extra space are you taking here? This is 1. This is 1. Is there any other variable extra you're using? This is 1. Input n plus 1. This is n plus 4 fixed space. So fixed space is in order of n, auxiliary space is in order of 1. Okay, that is bubble sort. Selection sort, right? Well, concept is this. Again, n minus 1 iterations only. During each iteration, what you will do is find minimum ith minimum element, and then once you find it, swap to ith place. So, for example, 2, 3, 5, 4, 1. Let's take the same example. 2, 3, 5, 4, 1. So, First, what you have to do is, I'll take take a different color. Iteration 1. Find minimum. That will be, you'll check for minimum. You'll find it as 1. Now you will swap these two. So this will become 1, 3, 5, 4, 2. Then next iteration, this is considered sorted now, the first element. This is your unsorted position. Uh, so from here, you will check for minimum. You will find it as 2. Swap these two. So 1, 2, 5, 4, 3. These two are sorted. Iteration 3, 1, 2. This is first unsorted place. And then you'll find minimum. You'll find minimum is this. Swap these two. 3, 4, 5. Again, next iteration will happen because it needs to identify which is minimum. So even though this is already sorted, the algorithm will not know that. It will keep doing till n-1 iterations overall. Okay. So it will find this as minimum, no sort. So this will be 1, 2, 3, 4, 5. So some key points are each pass, n comparisons are happening to find minimum, n-1 passes in total. So again, order is in n square complexity. So best case is n square, worst case is also n square. Let's go through the algorithm. Um, okay. This is cost 1. This will happen um, uh, n-1 iterations plus 1 n times this will happen. How many is this? 2. For each iteration, this cost 1, this cost 2. Again, same way of finding out cost here also. I'm not going to go through that again. But I will explain the algorithm though. So for each I, you're going to find minimum. This is the bunch of code for finding minimum. Uh, this you already know. I'm not going to explain that. Once you find the minimum, if it is not in the correct position, you will just swap. This is min, this is swap. And then this will happen n-1 times total. This cost n into n-1, right? So that is selection sort. Let's go through space cost also. Here, extra variables. Which ones? I contributes 1. Min index contributes 1. J contributes 1. Is there anything else? Temp contributes 1. Here again, array contributes n. N number itself contributes 1. So fixed space cost is n plus 5. It's an order of n. So space cost fixed is order of n, auxiliary is order of 1. Sorry, O of 1. Then last sorting algorithm we'll cover is insertion sort. The idea here is to have an incremental algorithm, right? That is, first consider one element, sort that. Next, consider two elements, sort that. Consider 3, sort that, till and do this till n elements, right? How do you do it? So again, this also is n minus 1 iterations only. So first iteration, consider this one element only. So it's okay. First, we'll consider two elements because obviously one element is always considered sorted on its own. So 2, 3. What you do is you compare this element with the previous one. If this is already greater, great, it is already in sorted position. Amazing. 2, 3, 5, 4, 1. So these two are sorted. Next, consider uh, along with this 2, 3 plus 5. So here we can see that this is also greater than 3. So let it be in its place itself. Okay. So 2, 3, 5, 4, 1. So till here we are considered sorted. These two we haven't touched yet. Third iteration, add this on to this. So 4 compare with 5. Is it 4 is not greater than 5? So swap these two. 2, 3, 4, 5, 1. Swap these two. Compare with 3 also. 4 greater than 3. Leave it right there. So basically, you have to keep swapping till you get to its position. Then add on 1 here. Is 1 greater than 5? No. Swap. Is 1 greater than 4? No. Swap. Is 1 greater than 3? No. Swap. See here, 1 there. Is 1 greater than 2? No. Swap. So 1 has also reached its position. By n minus 1 iteration, everything has reached its own position, right? What you can do is um, when you yeah, so it will take n minus 1 iterations. So again, this will be in order of n square. Best case. Okay, consider this, right? What if the array is already sorted? What do you think is going to happen? What will happen is um, 1, 2, 3, 4, 5. Even though no swaps are ever going to happen, it will check at least once for all these n minus 1 iterations. One check is going to happen. First iteration, this check happens, no swap. Second iteration, this check happens, no swap. This check happens, no swap. This check happens, no swap. So best case complexity will become O of n. Worst case complexity here is if it is in reverse order. Each time it will need to go all the way over there, all the way over there like that. That will be O of n square. Let's see this. So this will happen once. This will happen n comparisons. Assignment cost 1 per iteration, 2 per iteration, n minus 1 iterations, right? 1 into n minus 1, 2 into n minus 1. This let's take a worst case, right? So I times, right? Yeah, should be 2 into I. Yeah, something like that. So here this will be 2 per iteration inner. This will also be 2 per. This will be n minus 1. This is all considered to be in loop. And this is 2. N minus 1 again. Again, you can compute this. It will be in terms of n square only. This will all come to like summing of natural numbers or something like that only. You can figure it out. Let's see for fixed space. Extra variables. I contributes 1, key contributes 1, j contributes 1. Okay, let me explain what is key here. Key is considered to be the unsorted element, I think.